Thanks for coming. My name is Gynvael Coldwind, and this is Mateusz Jurczyk. We would like to present the, Bochspwn research, which actually got us a Pony Award yesterday. Really cool. So, at first I would like to say I'm sorry, we have a lot of slides and I'm not going to go through all of them. They will be made public, so the pieces we skip, which are basically basics of instrumentation, they will be available later for you to check out. But what are we going to talk today? We are going to actually start with the end. We are going to start with a demo of one of the bugs that we found during this research and actually show that what can it be used for. And then we are going to go about kernel instrumentation, system-wide instrumentation, and present our results and how we approach instrumenting Windows, Linux, and FreeBSD. There are also some slides about OpenBSD, but it's still work in progress, so we are not going to talk about it. Then we are going to talk about potentially about Hypervisor project and about and I will give you a sneak peek on Bochspwn MSAN, which is basically an extension to Bochspwn, which we are going to probably talk about later this year, and which already has some results. So let's start with the demo.
Hey. Okay, so the demo is live. I hope it works. We have a Windows 7 32-bit virtual machine here, which has the latest patches until January this year. So it doesn't have the February ones, in which the vulnerability that I'm going to show here was patched. So we log in as the guest user, and we basically have the exploit here on desktop. So we just run it. I guess I have to make the font a little bigger. Okay, you should see it now. So what happens here is that we perform some basic pre-initialization to find the symbols in kernel that we need to exploit this, and then we spray the user address space, run some program, and basically when I click enter, there is the exploitation of a race condition that we detected using Bochspwn. We had like 10,000 iterations to make sure that the race condition is actually that we win the race condition. And then after this, I hope we won the race during one of those races. And it turns out that we actually did. So we have root or anti-authority system on the machine. We can also check this out using Process Explorer. I think. Just a second. Yeah, so you can see that the process was elevated to anti-authority system. And that's it. That's a privilege escalation vulnerability for Windows 7 32-bit found by Bochspwn.
Okay, so probably some of you are asking like what happened, and we are going to explain the bug, and we are not going to talk how it was exploited. It's in our paper that we released some time ago. But first, let's talk about instrumentation. How did we find this bug in the first place, and all the other like 37 bugs we found during this research? So, you probably all know what instrumentation is. Basically, you run a program or run anything, run some code, and it has a set of states, and you cherry pick some of the states and examine them, monitor them, maybe change them a little, maybe like compare two different states. And thanks to that, you get some information which you can reason on. What exactly you are reasoning on, we are going to talk later. So as said, I'm going to skip the basic of user mode instrumentation and get to the point to actually kernel mode instrumentation, system-wide instrumentation, which we focused on this project. So our initial assumptions were that we want to instrument modern operating systems, that is Windows, that is Linux-based systems, FreeBSD perhaps, and other BSDs, maybe even OS X. And we will do this for modern operating platforms, which are modern desktop platforms, which are x86 and x86-64. Ideally, we wanted to instrument per instruction if possible, maybe per other event like per memory access. And actually, it turned out that it worked. So how do we instrument? Well, there are several options we discussed. The thing you see here is actually Box. Box is an open source computer system emulator, so it emulates both x86 CPU, it also emulates the hardware. And as you can see, it actually can run Windows and StarCraft 1, but it has some problems with VGA color palette, but that's actually not a problem for us, it works. So Box is awesome because it has all the CPU logic implemented in it. That means that if we wish to change how one instruction works, we can do it. If we wish to monitor access to linear memory, no problem. So that's great. We have 100% control of all the computer system, everything that's going on in the computer system. It's really easy to develop instrumentation for Box. It has an API, and it's pretty easy to debug because in the end, Box is a user mode application. So you just attach your favorite debugger, userland debugger, and you can debug it. However, it's extremely painfully slow, as in how slow I'm going to talk about later. And it's limited to virtual hardware. So it has some emulation for like old hardware, and that's it. So there is no chance of testing modern motherboard drivers or modern graphic cards drivers. Other approaches include, for example, using hypervisors, as in hardware virtualization, be it VTX or AMD SVM. A thin hypervisor is really nice because it's first of all, it has an extremely low overhead. It's really, really fast. And it allows you to run on real hardware, which means that you can test all the modern drivers as well. The problems are that it's kind of tricky to implement, especially when comparing to Box approach. And it might be difficult in debugging, especially if you don't own a hardware debugger. And it's partly, system specific, and it's also CPU specific. So that means if we focus on Intel, it won't work on AMD CPUs. It also doesn't allow you to change the logic of the CPU. Another approach would be, as you can see on these pictures, these are actually two laptops connected with a FireWire cable and running Windows and debugger. So basically, you use an external debugger to instrument the running operating system. This is a pretty sweet approach, I think. It's relatively easy to implement, especially if given external debugger supports a scripting language, like for example Python for WinDBG. It has relatively low overhead in comparison to Box, and it can run on real hardware. However, it's still slower than a hypervisor, and it's really system specific. So you either instrument WinDBG or you do it for KDBG or so on. And it's also limited. You cannot change the logic of the CPU. Another approach would be, using x86 trap hijacking. This is the method that Soft Ice use, if you know Soft Ice. It has a pretty low overhead. It allows you still to test real hardware, and it's pretty debuggable. However, it also is tricky to implement because if you ever have written implementation for x86 traps, there are some things you need to handle properly. It might not be very elegant, and it might be a little system specific. And it's also still limited to what the CPU allows you to do, to what traps it actually issues, what exceptions it issues, and what it allows you to set. Another approach, a hardware debugger. The biggest problem with it is that we don't have one. So they actually cost some money. All the other approaches we mentioned, don't cost money, except for the FireWire cable, which is pretty cheap, of course. And so we're really unsure about also the scripting capabilities, and but it probably should have real, close to native speed and access to real hardware, so you could test real drivers on it. So the winner and our things we picked, as you know from the name of the talk already, is Box. So again, Box is a full computer system and full CPU emulator. It supports all the modern features and CPUs, including virtualization, so you can actually run VMware inside Box. This is awesome. And it provides an instrumentation API. So it's not really a plugin API, it's actually a set of defines which you implement, and they get called on certain events. So when are the events called? Well, there are actually quite a lot of events in Box that Box already has instrumentation provided for, and since it's open source, you can of course modify everything that's not exported into this instrumentation API. So a couple of things that are useful when you instrument stuff. First of all, this is the basic stuff, well, really basic stuff, like Box starts or the guest machine gets rebooted, you get one of these callbacks called. This is more interesting. This is actually for basic blocking instrumentation. So there is a branch taken, branch not taken, far branch, and so on and so on. So you get an event when a jump happens in the guest machine. You get a callback. There's also, of course, instrumentation for exceptions. So when exceptions happen and you get a callback, you can, well, check the state. And this is a really interesting one. It's basically like single stepping in classical approach. So you get notified before one instruction is executed, when it's already decoded, but before it's executed and emulated. And then you get notified after it's executed. This is quite important in our research, and we are going to talk what's it for later. There's also, of course, memory access. So a program has an instruction that accesses linear memory or physical memory, and you get notified. That's really useful for our research as well. About performance, well, this is the short story. As I said, Box is painfully slow, and by painfully slow, I mean from 80 million instructions per second if you have no instrumentation and you have a really modern CPU, then you get an 80 megahertz basically machine. So, well, running Windows on it is kind of slow. It boots 4 minutes, I would say. However, if you start instrumenting things, if you start adding your well, instrumentation to it and all the logic, it gets slower. In the end, you might even decrease to like 1 megahertz, but actually most of our instrumentation runs about, I guess, 20 megahertz. So that means that Windows boots 20 minutes. Linux is not too much faster. FreeBSD thankfully was. So, well, it's okay for research, especially if you have automated tests, but not, well, you cannot do normal work on it, of course. So we can instrument anything in the operating system. Anything that happens in the operating system, we can instrument. What shall we start with? And Mateusz is going to talk about double fetches, which we focused on.
Okay, so let's start with double fetches, the condition that we focused in our research primarily. So what double fetches are, they are basically like time of check, time of use type of bugs where the kernel assumes that a specific memory area within the user address space doesn't change or is consistent between two different points in time. It's basically probably a bug because the kernel cannot really know whether a specific place within user address space hasn't been changed by a concurrent thread on another CPU in the meantime. So whenever it does that, we have a bug in the kernel. So that's what we're looking for. And the whole research started with this bug in Win32k that we found using manual analysis, as you can see here in the code snippet. We have the ECX register which holds a user mode pointer, and then it is basically used twice. The first time it's used to fetch the pointer that is being validated, and then it is used again to fetch the value to actually use it. So we have a double fetch with 2 fetches within 3 assembly instructions. And when we performed some variant analysis over it, we found out that there were 26 different instances of the very same bug all over Win32k. So we found this in Q4 of 2012, and we reported this to Microsoft immediately, and they fixed it in February this year, along with some other bugs. And this particular vulnerability allowed us to read any memory within the kernel address space. So this was an information disclosure vulnerability. So when it comes to the trivia of double fetches, they usually occur within consistent code blocks. So either within like single system calls or IOCTL handlers, or in general like consistent code blocks that are invoked from user mode. And if you find a double fetch, the maximum impact that you can get from it is local bugs. You cannot really find remote ones because of the fact that in order to actually flip the user mode memory that is being rainsed against, you actually have to have code execution to have a thread which flips the value continuously. So in the worst case, a double fudge vulnerability can lead to an elevation of privileges if you manage to get it to trigger a condition such as a buffer overflow or a write whatever condition. You can also end up with an information disclosure such as the bug that I showed before, either by having arbitrary reads into the kernel mode if you operate on pointers or maybe underfield buffers that are being copied back into user mode. And you can also basically have like all sorts of denial of service if you fail to exploit either of the two previous types of issues. So exploitation of race conditions like that are not really the subject of this talk because, well, it's a whole different thing. We already addressed it during our syscall talk this year, and there have been also some exploitation technique detailed by Esgracu and Twiz in 2007. So be sure to check out our slides and white paper from syscall and also the two guys' work, which is an article in FRAC. When it comes to detection via instrumentation, the general idea is as follows. There are three major steps that we perform. The first one is to collect all information about the memory accesses that take place throughout the whole lifespan of an operating system. And after we have that information, what we do is that we find all pairs of memory fetches that take place in kernel mode and read from user mode memory such that they meet three conditions. They are within the same thread, they are within the same system call invocation, and they access obviously the same memory location. So after we have all of these pairs, we basically filter out all of the known false positives, and there are usually lots of them, and then basically manually look into all of the reports that we got and find the actual bugs. So as I said, we have to have a large database of memory accesses, and each memory access can actually be characterized by quite a lot of information which we need to implement the logic of the double fetch finding. So we can actually group all of these types of information into several different types of things. So we can characterize them by purpose. So we have three different purposes of this information. The first one is information that is actually required to implement the logic. So this is the essential information that we have to find out if the memory pairs meet the three conditions that I mentioned earlier. So then we have the types of information that we have to actually perform double fetch analysis after we find the double fetches, which help us actually understand what is going on in the code, such as the instruction disassembly or the number of the system call and stuff like that. And then we also have information which helps us find the unique issues so that we don't end up with a list, like a long list of duplicate issues. We have to have the stack trace to find out which cases are really the same bug. And we can also group these types of information by the source of where we take them. So we again have like three groups. The first one is information that is provided by the linear memory access callback that we have from Bochspwn. Then we also have information that we get from the other type of callback, which is the one that is invoked before the instruction is executed. And we need that because we have to know about all system calls that take place within the operating system. And we do this by looking for the systenter instruction or the other instructions that are used to invoke system calls. And after we find an instruction like that, we basically examine the EAX register and find out which system call is being invoked by the user mode program. And then we have the third type, which is basically the information that is stored within memory of the operating system that we have to read basically directly from RAM. So our implementation is as follows. We basically create a large memlog bin file that contains all of those memory accesses. It's usually like many gigabytes because there are lots of memory fetches within the operating system lifespan. We split the file into thread-specific logs, so we end up with thousands of log files, each corresponding to each thread that was running inside of the system. We run the double fetch utility over each of them, and after we have the output, we symbolize the resulting reports and perform unicization and then look into them. So here you can see the exemplary report that Bochspwn generates, and as you can see, you basically have a nicely formatted information that I mentioned earlier. So you have the ID of the thread in the form of a process ID, thread ID, and creation time or some other characteristic of the thread. Then you have the process name, you have the type of the memory access, its length, the instruction disassembly, and the full call stack. this is basically a report for Linux, but the ones for Linux, so for Windows and all other platforms look basically the same. So even though the idea for detecting double fetches is generic and applies to all operating systems, there are many system-specific things that we need to address. So like there are different distinctions between what user mode and kernel mode memory is. And we have different system structures to traverse to fetch the data that we need to fill in the information about the context of the read. We have also different ways to actually generate code coverage of the kernel and different false positives that we need to filter out, and obviously different results. So we need to look into all of these platforms separately. So let's start with Microsoft Windows, the most interesting part in my opinion. So when it comes to the distinction between user and kernel mode, it's really simple in Windows, because you have the entire address space is basically divided into two parts, and you can use a less than or greater than operator. So you can see the memory boundaries here. They are different obviously for 32 and 64 bits of versions of Windows. So that's a really simple part. Then when it comes to traversing the structures that contain information about threads and processes, it's a little more complicated. As you can see, we basically traverse three structures. First, the kpcr, which contains a pointer to the current thread, which in turn contains a pointer to the current process. And we get the pointer to kpcr using the base address of the FS segment on 32-bit Windows, and the base address of the GS on 64 bits. And then the three structures actually contain all the information that we need. So the IRQL level and the information about the current thread and the image name of the current process. And then when it comes to getting information about all of the drivers that are being loaded by the operating system, which we need for symbolization, it's also pretty simple. So you have to get the address of the first item on the LDR module list. So you get that using like traversing two different structures on 32-bit version of Windows, or because of the fact that one of these pointers is not really present on 64-bit version of Windows, we just hardcode the offset of a PS loaded module list pointer within the kernel image. And then after we have that, we can read information about all of the kernel modules loaded in the operating system. So this is also pretty easy. So when it comes to the false positives that we encountered when we were running Windows on Bochspwn, there's quite a few of them. So the first ones are, the first one is reports originating from the system process, which is the most important process in Windows. It is a kernel mode process entirely, and its main activity is when the system boots. So at this time, during very early boot up, there is no user kernel boundary yet. So we ended up with lots of false positives because of this. And we could easily discard all of these false positives by just ignoring all reports that were coming from process ID equals 0 or 4, which is this specific system process. We also got lots of false positives from APC related kernel routines, which we neutralized by discarding all of those fetches that were taking place at IRQL equals APC level. Then we had again lots of reports originating from the CIDLL, which is responsible for handling the signing, the PE signing things. So we just removed all database entries which had ci.dll somewhere in the call stack, which was also pretty effective. And then we had numerous false positives in the messaging routines of Win32k, which we basically had to deal with by having a blacklist of known functions that are known to have false positives. And the most prominent thing of false positive that we have had to deal with was memory probing, because you probably know that the Windows kernel, one of the Windows kernel design decisions is that before using a user provided pointer, you actually have to probe it to find out whether this is a valid pointer and points to mapped memory. So you have several public functions to do that, such as probe for read and probe for write, but it turns out that the kernel itself also has several internal functions for that and internal macros. So the two most prevalent patterns that were responsible just for doing the probing are the two listed here. The first one is for checking whether the memory is writable, and the other one for checking whether the memory is readable. So the first pattern was mitigated by logging all 4 bytes write accesses in addition to the read ones. And then we could use that additional information to filter out all of the patterns where there was a 4-byte read followed immediately by a 4-byte write, in which case we just figured that this would be a probe and not a real read. And the second pattern was mitigated by just ignoring all reads of less than 2 bytes, because it turns out that there are so few legitimate 1-byte fetches from user mode in the kernel that we could just safely ignore them. When it comes to symbolization, this is really trivial for Windows as well. So Microsoft supported debug help DLL, which has all of the necessary API for doing the symbolization. There are basically 3 functions that you need to use for that. And you also have to have the PDB files for all of the kernel modules that you want to symbolize, which you can basically download from the Microsoft symbol server. So it's pretty trivial to implement one's own resolver with that information. Okay, so when it comes to the results, we had like 5 different iterations running Windows 7 and Windows 8 in different bitnesses, and all of this resulted in almost 90 potential new issues, which we all reported to Microsoft. Part of those were the initial 27 bugs that we also discovered, and we reported them to Microsoft throughout November last year to January this year. And these resulted in the fixes of 37 EOPs being addressed by 5 different Microsoft bulletins. 13 issues were classified as only DOS, and I think were not fixed. And then 1 big problem is still being worked on as far as we know, and 3 other cases are being reinvestigated by Microsoft. So the rest were either assessed non-exploitable or non-issues or requiring administrative access, which is not really considered an elevation of privileges and stuff like that. So these were the official results. The less official results are that, well, Microsoft was obviously very, very receptive to the reports, and we also have evidence that in addition to just taking our reports and fixing the bugs, they also performed like extensive variant analysis of them, because we were continuously finding examples of routines that were around those that we found bugs in, and they were also fixed even though we didn't report bugs in those. So there are some exemplary symbols there. Also 3 of our original reports were fixed as variants with no CVE assigned, but we really don't have any idea of how many of those bugs were fixed as variants, or how many bugs Microsoft found internally, because we don't have that information from them. We also shared Bochspwn with Microsoft, but we don't really have an idea whether they are currently using it or not. One interesting thing about the whole research is that we decided to release all of the logs that we generated for all of the platforms, including Microsoft Windows. Specifically, we're releasing the reports that we reported to Microsoft. So one of the reasons is that Microsoft assessed a majority of the reports as DOS or non-issue, and we don't really have the resources to find out whether this is true or not, so we just let you decide. And yeah, so we also figured that since some of the Windows issues haven't been fixed for 9 months now, that's enough time. So we would like to warn you about those. And obviously logs from the other systems are being released too, so you can see the Linux reports and the FreeBSD reports that we got and look into those as well. So final thoughts about Windows is that it's generally designed very poorly and written poorly with regards to this specific problem. So Windows really lacks several mechanisms that are found in other operating systems. So we don't have pointer annotations so we don't really know for a specific function whether a pointer that it takes is a user mode pointer or not, whereas Linux has a user mode annotation for pointers. You don't have dedicated fetch functions that you could use to get data from user mode. So instead of that, you just use the pointer in whatever way you want directly. And there are also no strict data fetching policies, so everyone will just do as they will, which means, well, bugs. So we think that bugs are bound to occur in this configuration and this lack of countermeasures. And the only problem we have with finding bugs with Bochspwn is that we have problems generating coverage because of the fact that this is a dynamic approach. We are really dependent on how much coverage we have, because we can only analyze the program states that are really taking place. So if we imagine that we found like 40 bugs by just booting up the system and running a few tests, you can imagine how many bugs there still must be if you actually manage to invoke all of the less used system calls and IOCTL routines and stuff like that. We think there must be tons of them. So when it comes to the code coverage itself, what we did is basically boot the system up, do some system navigation like run Internet Explorer and some other default tools that we found in the Windows installation, and then play some multimedia, start StarCraft 1 as you could see before, and run some wine conformance tests, but we figured that's way too little. So if you have any ideas of how this could be still improved, we'll be really happy to hear from you. And our current belief is that if we have a moderately smart system called Fuzzer, we could really dramatically, like maybe twice or 3 times, improve the code coverage that we have now. So we are currently working on that, and maybe some new Windows bugs will be found and reported soon thanks to this. So there are some statistics regarding the code coverage that we have right now. You can see basically like what are the orders of the sizes of the code coverage that we have. Like we can see the code coverage for the 2 most important kernel modules, so the base kernel and Win32k, which is the graphics subsystem. So it's not really high, as you can see. The blue part is the code coverage that we got by just running, like booting up the system and terminating it, and the green one is for running the system and running all of the tests that I listed before. So for Win32k it's not really that bad, it's like 50% coverage, but there's still much room for improvement. Then we have the statistics for the system calls invoked, which are really similar to the previous slide. And then we also have the number of fetch instructions that we actually detected in the base kernel, in Win32k, and then in the all of the modules. Yeah. So that was about Windows, and now back to Gynvael about Linux and BSD.
Okay guys, so the last slide is really important. You can see how many fetch instructions are in Windows. Let's compare it with what we have in Linux. So how did we approach Linux? Well, first by Linux I mean actually Ubuntu 13.04, 64-bit with a generic stock kernel. And well, when you approach instrumenting, when we actually ported Bochspwn to support Linux, we needed to address a few things which Mateusz already mentioned, both for Bochspwn and for Windows. So first of all, we need to gather thread information. And important thing to realize here is that we might get an event when the guest is in user mode, and we might get an event, a callback, when the the guest is in kernel mode. So first we need to have, well, actually 2 different approaches. So to get thread-specific information, if we are in user mode, we actually just, read the task register, go into the TSS, these are of course x86 structures, and read the kernel RSP, kernel stack pointer. That's important on Linux, read the stack pointer from there. However, if you are on ring 0, this is trivial because you already have the stack pointer in the stack pointer register, obviously. Once you have this, well, Linux is quite interesting. You actually have the kernel stack for the given thread, and the stack pointer points somewhere here, right? And you mask out the lower bits, and you get the address of the beginning of the stack. And at the beginning of the stack, there is a thread information, thread info structure, which contains the pointers to information we need. So if we dive deeper, we actually read a task pointer from that structure, and we have the task structure. We read the PID. So this is interesting actually. Do you know that in kernel mode, I'm actually a Linux noob, so this was surprising to me. In kernel mode, the PID is actually the thread ID. And the TG ID is the thread group ID, which is actually the process ID. Confusing. Okay, com is the name of the process. The second thing, so this is already all the information about the threads we need. Now the modules, so the drivers. This is quite easy. So Linux doesn't have any kernel mode ASLR, so we just hardcode the address of the module's global variable, and it points to the beginning of the modules list where we can, well, read the name of each module, the address in the kernel where kernel mode memory, where is it, and the size of it. So it's basic memory forensic stuff, basically. So now the call stack. We actually want a nice symbolized call stack. Thankfully, the stock kernels came with frame pointers. They were not omitted, so they were in RBP or saved on the stack, which makes things really simple since you can just walk through it. However, we noticed that sometimes there was an entry missing. So if you go to the do exec v common function, you couldn't find a call to this to get user. There was some more function, one more function actually called, and that one more nested function had the call finally to get user for. And what happened? Well, actually, the functions that are implemented on Linux in assembly don't preserve the stack pointer on, the frame pointer on the stack. That means when we walk through the frames, we actually just skip one. And so actually, we solved it by creating events, actually getting callbacks when one of these functions was entered, save the return address, and then when we need a call stack, we inserted that return address in between the first and the second entry in the call stack. Another problem were inline functions. So actually, when you compile with inline, you get the symbolizations gets really messed up. This is easily solvable if you recompile the kernel by disabling inline at all. So speaking of symbolization, actually symbolization on Linux is trivial as well. You just, in case of Ubuntu, you just download the symbols for your stock kernel, which we did in our case, and there is the GNU binutils address to line tool, which we written a simple Python script to run it, and you get from addresses you get it translated to file name, line in that file, and the function name. Okay, so we have symbolizations, we have thread information, we have module information. Now how do we get the coverage? So we run fuzzers. Fuzzers get sometimes decent coverage. We run I know this, Trinity, fsfuzzer, and some others. And we also run the Linux test project, which is a really cool set of tests. In the end, we got a coverage on the level of, I guess, 28%. This is, by the way, instruction granularity in the kernel. It's, I would say, 1/4. And 301 system calls were called in the end. So it's far less than Windows has, as you know. So in the end, when we ran Linux on Bochspwn and started generating logs, like the memlog.bin file that Mateusz mentioned, we got logs up to 200 gigabytes. So you can, I guess, imagine how many hard drives we had to buy during this research. Actually, quite a lot of terabytes went to storing just the logs. There were about 50,000 threads run during this research, unique threads, and the output filtered logs, the double fetched logs, were from up to 200 kilobytes of text data about double fetches. Yeah. So final results. I guess there are some Linux fans here or people who just cheer for Linux. How do you think Box performed against Linux? So there are actually 3 digits here, and I'm going to reveal one by one. So how many hundreds of bugs did we find?
300.
Actually, no. Actually, not. It's not in the order of hundreds. It's neither tens. Actually, we didn't find any bugs. Yeah, so it came as a surprise for us. As I said, I'm a Linux noob, so I thought it would be, same as on Windows. But why is that? I mean, let's do some documenting failure stuff. So first of all, there are actually 3 reasons. Because we analyzed it, we said, well, there should be bugs. Why aren't there? And there are 3 reasons. First, they don't just randomly dereference pointers as they did in Windows. They actually have a lot of copying functions which are needed to be called to read data from memory. And as you know, well, developers are lazy basically. So that means that if they can dereference a pointer, they will do it. But if they need to call a function, then probably they would prefer to do it once instead of twice. The other thing is actually sparse. Sparse and annotations. So this is a user __ user annotation for all the input variables and fields and structures that a system call gets from the user memory. And if the variable has annotation like this, it cannot be dereferenced. A dereference will basically issue a sparse warning. So this kills most of the bugs, or if not all, I would say. And the third is overall design. I mean, the structures are pretty flat that you pass to the kernel. There is no, they don't go deep and deep and deep. They are pretty flat, and this is a good design. What can I say? So that doesn't mean we didn't detect any double fetch conditions. We did, actually a couple of them, and but there are no exploitable ones. I'm going to talk about one in do TCP get sock opt. There's a get user length. It gets an opt length from this pointer, gets the length, the integer to this buffer, to this integer variable. And then does something to it, calculates a minimum value. And then again, if you go deeper to the function, there's a switch case, and then sometimes, in some cases, you get again the fetch. However, due to how this variable is used, you cannot do anything malicious with it. You cannot actually use it to get root. So, well, it's basically a false positive in terms of vulnerabilities. So that's about Linux. No bugs found. We are still going to work on it and work on the coverage especially. Maybe we'll find something. And we also have some other approaches we are going to test against Linux. So, FreeBSD. We used, well, 9.1, 64-bit generic kernel. Again, when you instrument, you have exactly the same thing. So you need to handle both getting the information about threads and if the event is from user mode and from kernel mode. Actually, we use the gs.base in this case for getting the thread information. You can read it either directly from the register in ring 0 or just read it from the MSR that is used by swap.gs instruction. So once you have it, you traverse down. You go into the thread structure, read the thread ID, go into the process structure, read the PID. This is actually the process ID and this is actually the thread ID, so it's not like name confusion like on Linux. And the name of the process. And if you would like also to get modules where you can do like this, same idea as on Linux, some more traversing deep. However, we didn't bother because it turned out there are 477 modules in FreeBSD by default registered. However, all of them, each and every one of these, is in the kernel image. So we can just assume that everything is in the kernel image and be done with that, and if this will really speed up with the instrumentation, because we don't have to like fetch data for 477 modules. So we ignored them. However, in the future, if we would like to test some modules, because FreeBSD actually supports external modules as well, we would probably need to re-enable the functionality. Okay, call stack and symbolization, same stuff as on Linux. One nice thing you actually have on your drive in the default installation the symbols for the kernel. That's a nice thing. You don't have to look for them and extract them. The coverage, basically same thing. Fuzzers, LF6 and Mateusz, FS fuzzer and Trinity ports from Linux. Stress 2 and regression tests for FreeBSD. So results again. What do you think? Well, it's not hundreds, I can tell you that. And actually you know where this is going, right? Again, nothing found. Again, we are pretty sad. So this is why I thanked Microsoft yesterday, because we actually have the decency to put some bugs that we can find. It means really a lot for us, like offensive researchers. Yeah, well, these guys didn't. No decency here. So, documenting failure again. Well, it has no annotations, but it has copying functions that need to be used. Actually 5 of them, so not a full slide of them like Linux has. This is a pretty nice design, by the way. And we've also been told that this is actually, double fetches is a pretty popular bug class on BSDs, on OpenBSD particularly, and also on FreeBSD, so well, this has been audited before. One false positive I would like to mention in kernel select function. So this is actually an actual report that we work on from Bochspwn. And there are 2 reads. First read is in select check bad FD, and it gets some byte. And then there's another one and gets the same bytes again. Actually, it gets bits. But due to the nature, again, this is a double fetch. But due to the nature of how this is used, it's not exploitable. It's just, it's not even a bug. It's not exploitable. You cannot do anything evil with it. Basically, a boring for false positive. There were also some other false positives. We are, as Mateusz said, we'll be releasing the logs on our blogs really soon, like I don't know, maybe tomorrow and in a few days. So you can take a look on the other false positives as well. I'm going to skip OpenBSD because this is still work in progress. There are some data on the slides if you would like to take a look. And we can also run Bochspwn versus NetBSD, maybe OS X, and maybe some other Linux distributions. We'll see. There is still also a lot of ground to cover with better coverage. Okay, now Mateusz is going to talk about hyperpwn and then about the thing that I find really interesting, and there will be one more demo, Bochspwn MSUN.
Okay, so about hyperpwn. So even though we had so much success with Bochspwn and Windows specifically, we found out that, or we thought that it would be interesting to actually have something much faster, which we could probably use, for example, on our workstation instead of just specifically running a guest on Box. So there are several very important advantages of this, such as all of the OS instructions execute natively instead of being emulated, and only instructions that we really have to intercept are being intercepted. All of the other ones are just running as is. And yeah, as I said, this could be potentially run seamlessly on anyone's workstation, so you could get coverage by just like working on this computer for a week or something, and just naturally expanding the coverage that we have. Yeah, but that's only if you don't really use VMs in your work, so I guess not for security people. Anyway, it's only very good for memory access patterns instrumentation. It's not really perfect for other types of instrumentation. So the initial concept that we thought of would be to start off with Jonah's Blue Pill project, which was basically a thin VMM that was loaded as a driver inside of the host system, putting the operating system in kind of a jail or a virtualist environment. As you can see here, this is the detailed design of that. So about how we would intercept the memory reads. So the basic idea would be to just instrument 32-bit operating systems, which are like the same code base as 64-bit, and do some GDT magic to really replace the data segment for the kernel, to have it like expand down with base 0 and size 8000, which would result in having the same base, such as the kernel's, all of the memory fetches would still work, but then an exception would be generated for all fetches from user mode performed by the kernel. So the VMM would that intercept the exception, perform the instrumentation in the same way as in Bochspwn, and then restore the data segment, set the trap flag, so the one instruction can execute and then continue. So this would be pretty straightforward. This is how we imagined this would work, but we really didn't think this through. So it turns out that there is no virtualization in protected mode, and on the other hand, there is no memory segmentation in long mode, so we cannot really implement this. But the revised idea would be to tamper with another part of the virtual address space translation mechanism. So instead of doing this magic with GDT, we could just do the same with page tables, as in clear the present flag in all of those top level page table entries, and restoring them after the instruction executes. So yeah, this is an illustration for that. Yeah, so we are still working on it. We hope that we will be able to present it in the fall of this year. Yeah, so be on the lookout for that. When it comes to double fetches themselves, there are some other things that we can do, like instrument Mac OS X and improve the coverage for Windows, which I already mentioned. And one other interesting things that we could do for double fetches specifically is try to approach them with a static analysis instead of doing dynamic analysis. And yeah, the symbolic execution model is fairly interesting for that. And we could also like try to mix the static and dynamic analysis by hinting the static analyzer with information that we have from the dynamic one, such as where are the instructions that we know for sure that are fetching data from user mode. So this could be interesting, and potentially it has much bigger capabilities of having like greater coverage, because then we're not limited to the code that we actually have to execute. Okay, so that's about Bochspwn, like the core of Bochspwn. And now we wanted to mention a project that we just wrote like a week or 2 weeks ago, and we also had some success with it. So what we wanted to really emphasize today is that kernel instrumentation is a powerful tool, and it's not only about double fetches, it's also about other types of bugs. So for example, we could think of like one potential application of that could be tracking, like doing chain tracking of kernel memory. So on 32-bit Windows, for example, or any other operating systems, you have like 1 to 2 gigabyte wide kernel address space, which is not too much. So like considering the current amounts of RAM that you can have in your computer, you can easily have like up to 16 bytes of shadow memory describing like a single kernel byte, which is a lot of information that we could store there. And so, for example, how about tracking the initialization property of heaps and pools and stack that are reside in the kernel and trying to find some bugs using this. So it turns out we could actually detect the use of uninitialized memory, which is like the an analogous thing to what memory sanitizer does in user mode currently. This is a very nice tool, which is an extension to CLang, by the way. So yeah, so we could really do that. We could also, in addition to just finding use of uninitialized memory inside of the kernel, we could also possibly detect the leakage of uninitialized kernel byte into user mode while the kernel is copying uninitialized memory into user mode. So we implemented a prototype for that, and we ran it against Windows just a week before this conference. So it turned out that it really works. We found like 12 bugs that are basically disclosure of kernel bytes from the kernel into user mode in both Windows 7 and the latest Windows 8.1 released just a few weeks ago. And we just did that by just booting up the system, so we didn't run any test, we just booted the system and found these 12 bugs. So I would like to show you a demo of the 0-day. We're not going to release the vulnerability, of course, because it's not fixed yet by Microsoft, but yeah. We can show the bug itself. So we have a Windows 8, and we are going to log into the guest account again. Yeah, we have the exploit here. So we just run it, and the font is too small again. Yeah, so you can see here is like kernel bytes that are being leaked from the kernel mode into user mode. These are not really interesting, like you cannot find any strings that you could recognize here or something because of the type of the pool that is being used here, but these are really uninitialized bytes. I could also, I guess, run it in another way to show you that this is really pool memory. Yeah, you can see like different structures of the kernel pool here. So yeah, you can see it works. Yeah, so that's a 0-day. This is going to be fixed probably in several months, but yeah. Anyway. Okay, yeah, we're probably going to discuss this approach in more detail later on, probably going to apply it for another operating system as well and get more coverage too.
Yeah, like Linux round 2.
Yeah, hopefully with more success now. Anyway, so the conclusions are, first of all, the most important part, I think, is that we are releasing Bochspwn as open source today. So the new name, the name of the open source project is KFetch Toolkit, and we are releasing the instrumentation part and the post-processing part, so basically everything that we use to discover all of those vulnerabilities that I talked about today. Yeah, this is on Apache v2 license. You have the link here so you can check out the project on GitHub and basically just refer to the README for instructions of how to compile and how to use it. There's like a 22-page document on how to use it. So there is also some further work to be done here. So we think that the kernel instrumentation is, the potential of it is like far from being exhausted. You can have many other ideas of how this could be probably used and find like hundreds of low-hanging fruit. So far it seems most of them are in Windows, but yeah, we shall see how the other ideas that we have now will apply to the other operating systems. So yeah, be sure to check the KFetch Toolkit thing and hack on it. Maybe port them to like another more exotic platforms or find other patterns that you could use to discover bugs, or improve the coverage, which is really useful again, or just test the other presented approaches. So we really hope that the subject will be picked up because we haven't seen too many people doing kernel instrumentation, and it's really fun. If you do have any problems or any results with KFetch Toolkit, just let us know. And check our blogs for slides and the double fetch reports that we mentioned earlier from our previous iterations.
Yeah, so this will be published in a few days, not now yet.
So thank you for coming. Thank you for your attention. Here are a few slides, a few thanks to the people that help us. And are there any questions?
Hello.
Hey.
Is this working?
Yeah, it works.
All right, so you mentioned things that cause false positives on Windows.
Right.
Did you find similar conditions for Linux or BSD?
Yes, so a couple of them were mentioned on the slides. So one pattern that we see on Linux, actually there's a copy string from user function, which tends to do a double fetch every time. It first checks the length, then allocates the memory and does the copying later. It's a double fetch, but it's safe. I mean, we've looked at it way too much. So yeah, when we publish the slides also, and the logs, there are actually a couple of more false positives mentioned in FreeBSD. For example, execv is commonly called with the first argument is the program name, right, the path, and also the same pointer is used in the argv table in the 0 element. And this is also a double fetch false positive because actually nothing can go wrong there, right? So I guess that's mostly it.
Do you have this in a paper or someplace?
So one paper on the methodology we published some time ago, you can look it up on our blogs. Then we don't publish a paper now, but there is a 23-page document on how to use the kfetch toolkit. You might want to refer to that. But we'll also publish the logs, and the logs have comments on them about what we think about a given report. So, well, that's not a paper, but there is some information there as well.
All right, thank you.
Okay, thanks guys.